Hey, what's up guys? My name is the Cherno. Welcome back to my game engine series. So last time we talked about shaders and we made them into asset files. Check out that video if you haven't already. And today we're going to be continuing on with our shader journey, making our shader API and library a little bit more robust, a little bit more powerful, because of course shaders are pretty much the basis of all of the graphics programming we'll be doing. So today we're going to be taking a look at shader libraries, something that I mentioned last time briefly. Basically, shader libraries are just, it's a way for us to literally store all of our shaders inside a library. So instead of us kind of creating a shader and then having that burden of ownership on ourselves, meaning that like, okay, well we need to store it like in a member function, like we need to store it as a member, or we need to pass it around certain functions, or we need to make sure that, we have like our standard shader that we want to render inside our like mesh class, for example, but we also want it in sandbox, we also might want it elsewhere in our code base. Instead of us having to do that, and instead of us actually like forcing the user of the engine to deal with that themselves, we're going to basically write a system in Hazel to deal with that for us so that we don't have to do that. I think that in general, it's good to have a robust engine API that provides the user of the engine, so like the client application, as much help really as possible, because if you're kind of writing an engine and it's kind of doing half of the job, it's not providing a complete library to the user to actually be able to do a lot of these common tasks, then it's just not as good as it could be. Because you have to think about it this way, right? We've written this little engine called Hazel, and it's going to be used presumably by a number of games to actually make those games. So by us kind of drawing the line and saying that, no, this kind of feature must be implemented by the user, right? Who is that user? You need to think about who that actual target audience is. Well, presumably someone using Hazel is going to be someone who is probably not an engine programmer, right? I mean, if they're an engine programmer, likely they're going to either write their own engine, or maybe like they would know enough about engine architecture and all of that to not even be relevant to this conversation. But most likely it's going to be someone who wants to actually use the engine. The vast majority of game developers out there are not engine programmers. And so because of that, especially nowadays, especially with kind of both Unity and Unreal making it super easy to write games, right? You don't need to worry about anything really. C# will kind of take care of itself in Unity, and then Blueprints in Unreal will kind of do all of the heavy lifting for you anyway. Of course, you might have to write custom C++ or whatever. That's besides the point. The point is you can make a game without that. And with Hazel as well, we will have a scripting language. So eventually, I guess my point is that it's going to be really easy to make games in Hazel. So suddenly, if you're kind of burdened with this kind of like, okay, it's really easy to make a game in Hazel, but if I want to do something with shaders, which you might not even have to touch, right? Like, I mean, shaders, you shouldn't have to do anything with shaders if you want to make a game in Hazel. That's kind of, you should just be able to draw something on the screen without touching a shader. But let's say you're a little bit more advanced, you want to maybe write your own shader, you want to kind of get into that land, right? Just like Unity lets you as well. But then you have to have this shader library that you have to kind of handle that stuff yourself. Now, what's going to happen from that is that a number of people are probably going to not know how to do this properly, or not know how to do this well, and they're going to write a solution that isn't as optimal as something that we could kind of think about and design and create right now. So what that's going to in turn produce for Hazel is basically it's just going to make the engine run worse. It might be more error prone, might have more bugs, it might just be slower in terms of performance, it might not be perfect, right? Because that is kind of a core system that we want to actually design ourselves, because we have kind of quality control over that. And then if someone uses this, again, if we talk about like something called the pit of success, which is basically the fact that no matter what you do, you should fall into that pit of success. Meaning that if someone just completely misuses this API and just writes something completely garbage, or just doesn't know how to use it, and so they don't do half of the stuff, the engine should still more or less succeed in giving them something that's actually not like the worst thing in the world, right? You shouldn't be able to put Hazel into a state where it's just like a crash zone. That's not what it should. It should be easy, right? It should be easy, it should be robust, it should just work. That's kind of the goal, I guess, of this engine, and probably most software projects that any of you guys should be working on. But my point here is that since that's provided for you, since that shader library is provided for you, you can just kind of use that. And of course, you can still write your own as the user. If you're like, I don't want this, I want it to work differently. If you know what you're doing, that's fine. Still want Hazel to kind of provide that control to people. But it's there if you want to use it, and it's kind of the right way to do things. And that's kind of why it's important to take a step back, think about these things if you're kind of designing your engine, and just do as much work as possible for your users, for your clients. Anyway, before we continue, I just want to give a huge thank you to all of the patrons that made this series possible. Patreon.com/the Cherno. If you guys help support the series, you'll get access to a private development branch in which I've done a lot of really cool stuff. And I've also been releasing exclusive videos just for patrons, which is just like a very casual kind of, almost like a vlog type thing, where I just kind of show my screen, back at my office, and I just talk about what I'm going to do in the next episode of this series. And I also show off a bunch of stuff from the Hazel development branch. It's a great way to help support this series and to make sure that these videos continue coming out. I'm actually considering increasing the frequency of these Game Engine series episodes, because as you can see, like, it's kind of, we just don't have enough time to get this stuff done in like the kind of half hour or 40 minutes that I try and kind of make these episodes every single week. So I would like to make these episodes twice a week. So huge thank you to everyone who does help support this stuff, because it's you guys who even make that possible. All right, anyway, shader libraries, let's dive in. And actually, before we dive in and take a look at this kind of stuff, I do want to mention that a few of you guys picked up on some things that I wrote in the last episode that were not very good in terms of code. So I did ask the question to do with std vectors. In fact, let's just jump in and take a look at the code. I think that'll be easier. If we take a look at the OpenGL shader.cpp file, when we wrote this code to do with compilation, we had this map that we took in, and I created this std vector, and I used the shader sources size as a parameter for this actual standard vector. And the reason that I did that was because I wanted to kind of have it, I knew what size I wanted the vector, and I didn't want it to dynamically allocate every time I push something back into it. So I thought, you know what, let's just do this to resize it. However, upon reading your comments, and then also actually reading the API docs for standard vector, I realized that actually that's not what it does at all. That actually physically creates that many elements. It doesn't just resize the storage, it actually resizes the amount of elements. So it's basically the same as calling resize instead of reserve, which is kind of what I was after. So you could fix this, and in fact, if we run through this, you'll see kind of what I mean. The problem is that this actually, and this will result in errors upon destruction, because what happens is GL IDs already has a size of 2. And they're both set to 0, of course, because you've basically default constructed 2 integers. But then when we go over here and we actually push back, what we're doing is we're pushing back a third element. And you can see that now at the end of this, and when we actually use this stuff, which is for this kind of unlinking stuff and detaching shaders, so we'll just go over here. By the time we get down to that line of code, this actually has 4 shader IDs in it, 2 of which are 0, which are garbage, so OpenGL is not going to like the fact that you're trying to delete stuff that doesn't actually exist. Or it might exist, it might actually be the wrong ones, but we don't, it's basically undefined behavior because we have no idea what's being stored at ID 0. And then 2, 3 are our ones, the ones that we actually want to detach or delete if the shader compilation failed. So obviously this is kind of not ideal at all. To fix this, really all you would have to do is come up here and either just get rid of the constructor at all, just so that you don't have anything in there, or if you still want to make sure that it doesn't allocate, and which is kind of what I was going for, you could just type in reserve and then a certain capacity, which of course would be shader sources.size. And if we basically put a breakpoint here and we just run this code again, and we see what we get here, you'll see that we reserve this as you would expect. The size is still 0, the capacity is 2, which is what I was after. And then if we go all the way down to our detachment of the shaders, you can see there's just 2 in there and you have the right amount. But this got me thinking, do we really need a vector for this? And the answer is no, because a vector, as you guys should probably know if you're not aware of how vectors work and how you can optimize vectors and all of that stuff, I have a few C++ series videos on that. Really important to check those out, because the thing is, a vector holds its storage dynamically. It means that when we actually create this vector, it will dynamically allocate storage for it, which is fine. I think that people probably go a little bit overboard with saying that heap allocations are bad. I mean, yes, they are bad, and we are designing a game engine, so whenever we can avoid them, even though this is certainly not the worst thing in the world, I would never ever like look at this and be like, this code cannot make it to production. It's fine. And in fact, it's quite nice because it means that if we have, it will work for any number of shaders, right? If we have 2, if we have 1, if we have 3, this code's gonna work. It's just gonna work because it's a dynamically resizable array. However, if we want it to be a little bit more efficient, what we could do is actually convert this to be a stack allocated array. And you can do that either by just using a C-style array, or we can just use std array, which is what I'm going to do right now. The downside to that, and look, I mean, if you could still technically keep that dynamic size if you wanted to. What you could do is, and by dynamic size, I'm not actually talking about the ability to resize, because there shouldn't ever be an ability to resize, really, for this. Because if you think about it, shader sources, we're taking in an unordered map. We know how big everything is. We do. We know that it's going to be 2 shaders, a vertex and fragment shader right now, because we obviously know about this because we're compiling the shaders now. We know how many there are. However, we don't know that until runtime. We don't know right now in terms of like compile time how many shaders we actually have. And in C++, if we want to have a stack allocated array, we need to know that stack size up front. So in other words, if I make an array right now, I have to say I want an array of size 2, for example. I can't be like, I'll just have an array of size shader sources.size. That's a dynamic runtime variable. We don't know that data until runtime. This needs to be known at compile time. However, there is a way around that. You could use a function called allocate. What that does, and I think I used that in the OpenGL series episode. Basically what that does is it performs a stack allocation. It's like malloc with the heap allocation, except it does it on the stack. Now, it's got a few differences. This video is not going to be about allocate, but it does have a few differences, such as the fact that, for example, unlike stack allocations, the scope of that allocation is the scope of the function of the scope that you're in, which in this case, if we allocated it where we did with the vector, it would be the same as the function scope. But also, some people claim that it reduces to it means the compiler can't optimize things as well, and that's, I don't know. I haven't personally run into any issues with that. So I would say go ahead. It's probably going to be better than this solution. But because we don't really need to resort to allocate, it's not like the difference is going to be we might have 1 shader, we might have 15, we might have 1,000. It's not like that at all. We basically are either going to have 2 shaders, maybe 3 shaders, maybe if it's a compute shader we have 1. The point is that the variance is so low, and these are GLenums. If we take a look at what GLenum actually is, it's an unsigned int. It's a 32-bit integer. Over a 32-bit integer, I'm not gonna cry about if we have like basically 4 bytes of storage, so 1 integer, or if we have 12 bytes because we have 3. That's absolutely insignificant, and it's going to be way faster for us to allocate that on the stack and have too many. So for example, let's just get 12 bytes of stack allocated storage, because that's 3 shaders, right? 3 enums, 3 unsigned integers. It's a lot better for us to just request 12 bytes from the stack. It's literally like you wrote 3 integers in your source code. Like you have a for loop, that's 1 integer, right? Maybe you have 3 for loops and just the indices, that's 3 integers, that's done, right? You don't think about that stuff. But when you're making arrays, it's tempting to be like, nah, that's too big or that's too small or whatever. But my point is that if we just write some code here that says, I want to allocate a stack array that has 3 integers or 4 integers or 10 integers, that is still going to be a lot faster than if we create this vector and then it does a heap allocation and it only allocates, I don't know, 2 integers worth, or you know how many it needs. So you shouldn't be worrying about that stuff. Let's just convert this into an array, because that's what it really should be. It should just be a stack allocated array. So what I'll do is I'll include that, because I'm not sure if we have that in the PCH. We really should. I'll include that in the PCH here. So we'll have array. My recommendation with this kind of stuff is try and use array whenever you can over vector, because using vectors liberally is not a very good thing to do because of the heap allocations. And of course, since we are kind of making an engine, it's really good to think about that kind of stuff. So what we'll do is, basically what we'll have is std array, we'll have GLenum, and what I'm going to do right now is actually write 2 for the size. Now this might be controversial, so to speak, because as I just mentioned, we could have 3 shaders, we could have 1, whatever, right? We basically need this number to be the maximum number of shaders ever. And to make sure that we never, don't do our job correctly, we're going to make a core assert here that basically says that shader sources has to be less than or equal to 2, okay? Because if it's not, if it's 3, for example, this code is not going to work correctly at all. So that's what we'll do. Then we'll, we'll just say that, I don't even know what to write in this core message. Basically that we only support 2 shaders for now, or something like that. I don't know. I'll get rid of the exclamation mark because it's really not that exciting. Okay, cool. So basically we'll just do something like this, and of course it's going to be shader sources.size. We're creating 2 of these here. We get rid of this completely, and now we need some kind of ID or index for them. So the easiest way to kind of deal with this is just to make a little int, which is just going to be our GL shader ID index or something like that, right? We'll set this equal to 0, and then every time we use it, we just increment it. So over here in GL shader IDs, we just do shader IDs, GL shader ID index ++. So we do a post increment because of course we do want to actually use it at like the value 0 first, and then next time we run it, it'll be 1, right? That has to be that size. And then we basically don't need to use it ever again, right? So that's kind of it, because over here, of course, we can iterate through it as normal. So what we've done is we've converted it to be a stack allocated array. We're just storing 8 bytes on the stack now instead of 8 bytes on the heap, which is going to be a lot faster, especially like the allocation stage. Not to mention that technically, whilst I would probably, we are using a lot of stuff here. You might expect the std vector to have its stuff ready to go in the CPU cache, but it might not be, whereas this definitely will be because it's on the stack. It's really hot and readily accessible memory, which is what we want. Anyway, yeah, this will work as expected. I'm not even going to really test it. It's definitely going to work. But if we look over here, when we detach them, for example, you can see that we have all of that stuff there. And of course, when that gets destroyed, we don't need to free anything from the heap either. It's all kind of just part of the stack that belongs to this function. Okay, cool. So that was just something that I wanted to mention. There was actually one other thing that I wrote that was incorrect. Very easy to make this mistake though. If we look over at the file reading, source code, basically what we had here was I used stdios in, and then I wrote a comma instead of an OR, bitwise OR operator, because this is actually all one parameter. This is a bunch of bit flags that says what kind of input stream this is. In meaning that we're opening the file as an input stream, so meaning read only, and then stdios binary, meaning we're going to be reading it as binary. I don't even know what that other, it just says in prod, like I'm not sure what that is. I actually did look at the API here. I didn't even find a third parameter, to be honest. All of these things have just 2 parameters, so I'm not really sure what that does. But anyway, as you can see, all of the modes, all of the applicable modes here, it's a bitmask type, so you can OR them together, of course, and we have in, which is open for reading, and then we have binary, which is open in binary mode. Okay, so that stuff is fixed up. Now that we've fixed up all of our code from last time, and we've kind of discussed why it needed fixing, and especially, like, I really wanted to mention that kind of vector array thing, because I feel like that comes up all the time, we can finally get into our shader library. So this is going to be very simple. Basically what this is going to be something that's owned by the renderer essentially, and that's good because it enables us to automatically load all of our default shaders, all of our kind of vital necessary shaders, which might include like diagnostic shaders, for example. We can load all of that stuff up when the renderer initializes, and then we can they'll be readily available in our program, and if the client or if the user wants to like load additional stuff, that they're more than welcome to do that. That will just work. And of course, because it will be kind of owned by the renderer, it'll be all static, which means that you can access it anywhere in your code base. So let's just dive in and write that code. So what I'll do is I'll go to just our normal shader.h file. So all of the shader related stuff is going to be in this file. I'm not going to create a bunch of files that are basically all going to be to do with shaders and call them like shader library.h. I think that that's just going to make the readability kind of difficult, and just having extra files is never a good idea. So what we'll do is underneath shader, we'll write a class called shader library. And the core to all of this, so we'll have, we don't even really need to have constructors or destructors, I think. The core of all of this is going to be an unordered map of string to a Hazel reference of a shader, right? So this will be our shaders, and I will include our unordered map. Okay, that's going to be basically all that this shader library is, and then we'll have a nice API to make it really easily accessible. So we'll have an add function which just takes in a shader so that we can add a shader that kind of exists already into there. So we'll just say const ref shader. The reason I take this in as a const reference, by the way, is because the copy, we don't really need to worry about copying this. It'll get copied. The actual smart pointer will get copied when we go into the unordered map. That's at which point we kind of copy it. So we don't really need to you know, make an extra kind of ref count here for no reason. That's why I like doing it this way, because I think that that comes up as well sometimes. So we can load a shader just straight up, because that would be kind of convenient, I think. And this should just return a ref, just in case we want it. So load will basically take in a file path. So const std string file path. And then what we'll do optionally is we'll allow people to just kind of name their shaders as well. So by default, the name that's going to exist is if we have a shader like texture.glsl, by default it's going to store it as texture. So it's going to strip the extension, strip the file path, any kind of directories that we might have like assets or whatever, it'll strip that and it'll just get that texture name out, and that's what the name will be. And that's what this string is. This string is going to be a unique name which identifies our shader, and then that of course is going to be the shader pointer. To support this naming stuff, we will have to actually add some stuff to the shader API, because of course at the moment if you add something with just a shader, you know, I don't want users to have to specify names or anything like that. And then we'll have to have some kind of get function, of course. So we'll have ref shader get, and then this will just basically retrieve something from that unordered map by just the name. Just like that. That's our entire API. Let's go ahead and create all of that stuff using Visual Assist, who I'm not sponsored by the way, in case you're wondering. But if they would like to sponsor me, I'm of course ready. So really the add function is just, what it needs to do is get the name of the shader out. So basically something like shader get name. This doesn't exist yet, but we need to add that. Once it's got it, it's going to need to check to make sure that the map doesn't already have a shader with that name, because if it does, then you know the shader is already present and we can't use that. And then otherwise, of course, if it doesn't, so I'm just writing some pseudocode here, then we basically just write, we basically just store it. So we'll say mshader's name equals shader, just like that. So the biggest thing right now is we need to somehow get that name out of that shader file path. So if we go to shader.h, not everything has a name, and that's probably fine. What we can do is when we create a shader pair like this, we can mandate to have a name. So we'll say const std string name. That's probably a good thing to do, because now that we're kind of storing these things as actual, like inside a shader library, it makes sense that every kind of asset should have some kind of ID. Now you could, of course, just store this as an ID. That's totally fine, but the problem is we want people to be able to access that. And for humans, strings are the way to go. So that's why we're using strings here. This is totally fine as well. And then what I'll do is just make a virtual std string, and it'll be a const std string. So we'll make the shader store it. Get name, and then const, and of course equals 0. Okay, so that's going to be our function. So we'll grab that. I'll grab all of it, and I'll go into glshader.h, and then over here, maybe somewhere around here, I will just do a const override. This will just return mname, which is something that shaders will now store. So over here, std string mname, and then if we come over here, actually, what I'll do is I'll add that name here, just like that. And then if we go into our source code, I mean, it's all source code, but I meant the .cpp file. So we'll have a name here and mname name. Okay, that looks pretty good to me. And then here we actually need to extract that name from the file path. So that's kind of easy to do. All we really need to do is, and I'm just thinking I might do this after everything gets compiled successfully. It doesn't really matter though. What I'll basically do is just do some basic string operations on that file path to get that stuff. So the first thing that I'm interested in is getting the last slash out. When you're doing stuff like this, it's really nice to just be able to kind of write an example for yourself so you can actually see what's going on. So we had assets shaders texture.glsl. That's kind of what we're looking at, and we need to select this. So if you think about it, what we need is that last slash, right? And then the last kind of, well, the last from the end, that last dot. So if we had like texture.shader.glsl, we would want to probably select this, right? Because that's part of the file name. And then the last dot followed by some letters is the kind of extension of our file. So if we have something like this, the last slash we can get really easily. All we need to do is just use file name or file path dot find last of. Make sure you use last of, not last not of. And then we can actually add a string here because the other thing you have to think about is on Windows, someone could actually use a backslash, right? So we need to handle that as well. So we'll just do find last of / or a backslash. So once we have that, we'll need to just make sure that that actually exists as well, because if you think about it, if we just have that, there is no slash at all, and that means that the last slash will be equal to std string npos, which means it wasn't found. So in that scenario, if it is npos, we just want to set it to 0. Otherwise, we want to set it to last slash +1. And the reason we want to do +1 is because if we don't do +1, then it'll just be the beginning index, of course, of this. It'll be the index of the slash, which is here, not over here, and we want it to be one past that. So that's how we get our last slash. The last dot thing is also quite easy to get. All we need to do is do file path. We could just do find last of as well, but there is another function called rfind. It's basically the same as find last of, but find last of will actually try and find any of the characters you give in your string, whereas rfind will kind of match it exactly, and we just need to find a dot, so it's better for us to use it in this case. And then once we do find that last dot, I want to use a function called, so we'll use filepath.substring, a function called substring, and what that takes is an offset and a count, not an offset, not kind of a beginning and an end index. So because of that, we can't just use this, we actually need to work out what the count is. So the count will just be, now the count will of course depend on whether or not we even have a dot, because technically a file doesn't have to have an extension. So in that case, if there is no extension, so last dot doesn't exist, right? So last dot equals std string npos. In that case, we'll just use filepath.size minus that last slash. So we're basically, again, if I bring back everything over here, assets, shaders, texture, what we're basically doing is if it's not found, so there is no dot at all, so that would look like this. We're basically just saying that the count is the filepath.size minus last slash. So this is last slash, this is filepath.size. So if we go back, we're just selecting this many characters, which in this case would be 7, which is exactly what we want. However, if we do have a dot like we do here, we basically need to go from the dot to the slash, and that's our count, because we're gonna start this filepath.substring. We're gonna start that at last slash, right? Because that's kind of here. And of course we set last slash to last slash +1, so it'll be perfect. And then we want to basically measure from that last dot to that last slash, how many characters do we have? So that simply becomes last dot minus last slash. And then that's it. We can just put that count in and we have our name. Just like that, okay? So this basically is to extract name from file path. Okay, cool, done. That's all you have to do, and we of course need to test this, so what I'll do is just put a breakpoint in here and hit F5. And of course, I forgot that we just modified this whole API, which is gonna wreck everything. So what I'll do is just fix up all of the API changes that we made. So we had file path over here. Sorry, we had name, it wasn't the file path. So we take in a name now if we create shaders like that. So that's actually gonna require a bit of a refactor, but that's fine, it needed to be done. Let's see what else we have. So array load, okay, this stuff needs to return stuff. We have get name now, so we can actually finish writing the shader library, and we'll test the name stuff at the end. So I just want to add a core assert here, which basically just verifies that that mshaders.find that our map doesn't actually contain that shader already. So if that doesn't equal mshaders.end, right, that means that we actually have that inside the map already. So we'll say shader already exists, okay? And then that way we know that we're trying to add something twice. For load, so this is a file path, it takes in a shader and it loads it. This is kind of easy as well. All we need to do is say auto shader equals shader create, and then of course we'll take in a file path. Then we'll have a name, so we'll grab this, and we can actually just do add with that shader once we have that. And then once we've added a shader like that, so this apparently still takes a pointer. I thought we changed this stuff, I guess we didn't. That's actually weird. Maybe I accidentally am not synced up the repository correctly, or maybe we didn't, in which case we didn't. If we didn't, we just needed to change this stuff to be a ref and not a pointer. So that's kind of easy to do. I think there might be some areas in which we forgot to do that. And then this becomes, I'm fairly sure we did this, but again, I don't remember 100%, so I'll just pretend that we didn't. So make shared and OpenGL shader. It doesn't matter, if we already did this, then that's fine as well. But it's the same, whoops, that did not copy correctly at all. Make shared, and then we have that. Okay, cool, so that looks pretty good to me. So now we just do add shader, and then we can just return the shader, because that's what load wants. So we basically create it, and then we add it, and then we return it. So load with a name specifically is going to do the same thing. It's just that instead of us adding it using the add function like that, what we actually have to do is add it by name. Just wondering, it's probably better to make a, and why would we specifically want, so that's maybe if we're taking a file path but we want to give it a custom name, that's fine as well, I guess. What I'll do is I'll actually make another version of this that takes in a name, and this is kind of going to be the same thing as the other one. So we'll grab, I'll copy this so that we can implement it ourselves, and then what I'll do is, so this will kind of be the, I guess the super ones, we'll actually put it ahead because we'll get this add to call that add. So what this will do is, I'll copy this, it's just that it's got a name, so we don't have to worry about getting the name out of the shader at all. So it's got a name, and then this will basically just call add with the name that it got and then the shader. So this way we support adding it without a name if we don't have a name. Or rather, we support adding it with a custom name instead of relying on the file name if that's what you want. And then finally get will be super easy. Basically, we'll just return mshader's name, but we should assert, of course, to make sure that it exists. So we'll say that shader, okay, this is wrong, actually. So I don't know how I missed that. So we're trying to make sure that it does equal end, right? So that means that we do not find the shader. In this case, we want to assert that it's not end, which means that we do find the shader. So if that actually asserts, then shader not found. And then that's it, okay? We don't want to waste time really doing stuff like if, handling it and maybe returning like a null pointer. You could do stuff like that, but the problem is that this assert will be stripped out in release mode. You probably should never have a state in which you request a shader and then it's not found. If that's really like an issue, we could easily add a function that that has something like exists, shader library dot, exists, and then just a name. And then in that case, what this will do, and we'll make this const, what that would do is just, if I implement it quickly, and then all that this would do is just return mshader's find, name doesn't equal mshader's end. So if it doesn't equal end, then it does exist, and that returns true, which is what we want. And of course, since you've written this code, you can of course just do exists and then name to make sure that it actually, you're asserting that it does exist. And then in this case, we'll replace this with doesn't exist. So not exists name, just like that. Okay, cool. And now we have a pretty functional shader library. So where does this deserve to live? Technically speaking, it should be something owned by the renderer. As you can see, we're in a situation here where we don't even have storage for the renderer. So I'll show you how it works in Sandbox. And then when we actually get into how the renderer is going to store all of its variables, which we haven't even covered yet, that's when we'll kind of deal with that. So Yeah, I think I know what happened here. I am on a, I must be on, I don't know, everything's fine. But these are all, yeah, I was so sure that we replaced this stuff. I may be on an old copy because what I did, stupidly, is I kind of nuked my repository because I thought I committed it, but I didn't. So I lost all of my local changes, and that might have included fixing stuff from last episode. So if that's happened, then I'm sorry. So this shader, I don't even know what this is. I don't think are we using this anywhere? M shader. We were using it for our triangle, so I'll kind of call it our triangle shader. See, this is good because it forces us to actually call our shader something. So we'll say vertex color triangle, maybe, because you can see that if you look at the source code, it kind of says our color to be based on the vertex positions. So, you know, vertex, maybe vertex position, vertex pos color, okay? So that's that shader, and then this shader, the flat color shader, that obviously kind of has a name, so flat color, I think everything else is good. Let's try and compile this code and see what happens. We still have a few errors inside the OpenGL shader stuff, which is probably fine. I may have just forgotten to do some things. So what's actually wrong with this? Something about overloaded operators, mname. That should be okay. I'm not sure why it's complaining. No instance of overloaded function, OpenGL shader matches. So, oh, right, okay. So I accidentally removed const here. That was probably Visual Studio, because sometimes when you type stuff, it likes to remove words around what you're typing. That's really frustrating. I should turn that off. But anyway, we'll hit F5 and we'll see what this gives us. Okay, cool. So everything's kind of working. One thing that I did want to check was whether or not that name was stripped successfully. So if we just look at this breakpoint and we look at everything else here, the name should be set to just texture, as you can see, which is perfect. It's exactly what we want. Okay, great. So now to use this shader library, what you need to do is, and this will be done in, eventually, of course, in our actual renderer. So this is not something that you would do in Sandbox, but basically we include shader. I think OpenGL shader includes shader, so we actually don't need to even include this. We basically set up a shader library. So again, really easy to do that, and it can totally live on the stack. So just shader library, just like that. And then what we need to do is every time we add a shader, instead of having to worry about holding references to it, and of course this is a Hazel shader library, instead of worrying about holding references to it like this, you can see we've got like M shader here, for example. We don't really need to worry about that at all. For our texture shaders, which, let's just, as an example, let's just get rid of that texture shader. So let's see what we had here initially, because we definitely had, so we had our texture shader. Where is that? It's over here. Let's get rid of it. So I'll show you guys kind of how, like, what this actually does. So instead of having M texture shader, what we really need to do is just do M shader library, and then we can just do load with just the file path. So we just kind of end up with something like this, M shader library load. And then if we actually want to access it, like we do over here, so load actually returns a ref. So we can just say auto, you know, texture shader or something like this if we wanted to. We put that in here, and then that's fine because that reference will die, and that's totally okay. What happens is when we need it over here to render stuff, we just say auto texture shader equals M shader library dot get, and then texture, just like that. And then we just replace this like this. So what this now gives us is the ability to actually store everything inside a shader library and then reference it as we need to. Now, in this case, it's kind of a step backwards, because instead of having a nice reference inside Sandbox app and just being able to render that and not have to worry about getting stuff out of an unordered map, even though that is super fast, instead of doing that, and instead of having a member, we've kind of resorted to doing this stuff, which is kind of not the best thing to do in this case, but of course you have to imagine the fact that you're not going to have everything in one file, in this one kind of example layer. Yeah, example layer. So instead of having all of this stuff here, you'll have it all around your kind of engine code and all around your game code. And then now what we've done is a way to access this. And of course, instead of having shader library, we might have something like a renderer get shader library and then get, just like that. So it would be a little bit more static and a little bit more accessible than having to have something like this, but you can see it works like this as well. So if you really wanted to have segregated shader libraries of just various groups or chunks of shaders, you can do that as well. We should probably test this, make sure it works. If we hit F5, then we should see that in action. And you can see we get exactly the same result as before. So in a nutshell, that is shader libraries. That's how they work. I'm not going to go ahead and replace every shader that we have with that specific like shader library version of that shader, because that's, for this example, it's not necessary. I probably wouldn't use it. But when we do have like a standard kind of 2D shader, or a standard like, I don't know, blur shader or some post-processing shader, and a standard like PBR shader, in that kind of case, that's when you actually would want to use the shader library. You'd have the renderer upon initialization actually load all of those required assets and resources like the PBR shader that it uses, for example. And then that would actually store it in the shader library so that it's accessible by your entire code base. And that's actually what Hazel Dev does at the moment. Anyway, I hope you guys enjoyed this video. If you did, you can hit that like button. As mentioned earlier, you can help support everything that I do here on YouTube by going to patreon.com/the Cherno. Huge thank you to everyone who is graciously supporting this series. Next time, look, there's so many things that we have to think about. I actually want to have a bit of a maintenance episode. I might have it as like a midweek thing. We'll see if I get the chance to. Just because there are a few things we need to kind of clean up here, and I want to deal with the repository a little bit as well, so we will see. But apart from that, yeah, we might have like, we are gravitating towards 2D, so I think that very, very soon we'll start kind of building up everything we need to get a nice 2D renderer into here. I'll see you guys later. Goodbye.